Okay, so thank you all for joining on the second day of this talk series on quantum error correction by Dr. Narayanan Rangaswamy. So Narayanan, over to you.
Okay. Thank you again, Prasad. Um, all right, so this is where we left yesterday. So I thought it's again a good idea to jog our memory on what all we saw yesterday. So we started with pure states. So we saw all operations have to be unitary. And then we defined polymatrices for a single qubit, and for many qubits, we just took Kronecker products, just like we did for the basis states of for pure states. And we saw that whenever you measure a poly operator, two things happen. One thing is you read a measurement, which is the eigenvalue of the operator, and then the state gets projected onto an eigenvector. So the post measurement state after you measure a poly has to be an eigenstate of that poly. And the eigenvalues can only be plus or minus 1 because the polys we consider are only Hermitian unitary polymatrices. Because they're Hermitian and unitary, the only eigenvalues are plus or minus 1. And then we saw that we defined entangled states, and then we saw that commuting polymatrices can uniquely identify a state. And if you have n qubits, and if you have n generators for the group, that's called a maximal commutative subgroup of the poly group, because any stabilizer group, remember, is a commutative subgroup. And if you have n generators for the group on an n qubit system, then it's called a maximal commutative subgroup or a maximal stabilizer. So a maximal stabilizer defines a unique state up to global phases. But if you have less number of generators, then there is a non-trivial subspace where you can store information. That's called a code. So the plus one eigenspace of a stabilizer group is called a stabilizer code. And so just like we did, so for poly measurements, so the same principle applies when you measure the stabilizers, which are polys. So the eigenvalue that you read is now called the syndrome. And you can map if the syndrome is non-trivial, you can map it to the most likely poly error based on considerations of your system. And a code can be uniquely defined in three different ways. You can either define the logical basis states, the logical computational basis states, meaning, so if you have k logical qubits, you define what is the physical n qubit state that denotes the logical 000 state all the way up to the 1111 state. So those 2 to the k, so if you have k logical qubits, you have 2 to the k basis states. And so if you define the n qubit code states that represents the 2 to the k logical computational basis states, then you have uniquely defined the code. Or you can define the logical polys, which is the most general thing we do. So you define stabilizers, and then you define logical polys as cosets of the stabilizer. So that's the most general principle. And or you can also give the encoding circuit, which is also not common to do. Finally, once you have defined a code, so you need to compute on the encoded information, and so you have to find lab operations, so physical n qubit operations that compute on the logical k qubits. So these are called logical operators. And we saw, so through this flow, we saw the example of this simple 3 qubit code which encoded one logical qubit, but it was able to only correct either X errors or Z errors. We defined 2 different versions of the code, and we saw that Peter Shor proposed to concatenate the 2 codes to get a 9 qubit code. So 3 times 3 is 9, so where you first encode into the Z flip code, and then you take each of the 3 qubits and encode it again into the X flip code. So by concatenating, he showed that you can correct any single X or Z error. And because we saw this discretization of errors principle, as long as you can correct the poly errors on a single qubit, you can correct basically any error on that qubit because of that result. Or at least there exists a recovery operation that can protect you from any error. Okay, so now the next thing I'm going to do is to generalize what we saw as examples to a general principle, a systematic mathematical formalism for general stabilizer codes. For that, let's again look at what the polymatrices were doing. So we had this X matrix, and the X is the bit flip and Z is the phase flip. So X was your classical NOT gate, and the Z was your, like, it was picking up a phase when acting on 1, and if it leaves 0 unchanged. Y is just a combination of the two, and usually we only think of X and Z. We don't care much about Y. And when you have multiple qubits, we took Kronecker products, and by the property of the Kronecker product, each Pauli matrix acts on the corresponding qubit. So X on 0, Z on 1, Y on 1. And we saw that Pauli matrices form this orthonormal basis. Okay, so now let's introduce a new notation for these Pauli matrices, which is super convenient. And I will mention before I introduce it is that, so this is the part that actually connects, that establishes a tight connection between quantum stabilizer coding theory and classical coding theory. So we are going to introduce a notation for the Pauli matrices. That is the main binary coding connection. Okay, so here we go. So this is some new material, but it's just a generalization of the material we have seen. So we have the Pauli matrices X and Z, and because, yeah, so on each qubit, if you only think of X and Z, you can either have X or not have X, and have Z or not have Z. So we just introduced two binary vectors, A and B. You can think of A as the X component and B as the Z component. So as the notation makes it clear, on each qubit, if the corresponding index in A has a 1, then you're applying X. If it has 0, you're not applying X. Similarly, if you have B, if the B component is 1, then you're applying Z, otherwise you're not. So this is just a simple binary notation. So given two n-bit binary vectors, that directly denotes a Pauli matrix. But note that, for example, let's just assume n equals 1. So just assume a single qubit. And let's say both A1 and B1 are 1. Then this DAB is just X times Z. But we know that X times Z is not Hermitian. So in order to make it Hermitian, we need to make it a Y, which means we have to multiply by I. And so that's why Hermitian Paulis have this EAB notation, where you take this DAB, and whenever both A and B are 1, you introduce an I. And this inner product mod 4 is doing just that. It is checking in which indices both A and B are 1. So EAB is what we commonly use because it's always nicer to stick with Hermitian Pauli matrices. But whenever it's convenient, you can also think of DAB. Now, so up to this global phase, both DAB and EAB are pretty much the same thing. So you did not worry too much about this thing for this talk. And let's see what DAB does on a basis state. So for a binary vector, this is your computational basis state on n qubits. So like we saw, A is denoting the X matrix, and we saw X is the NOT gate, so it just flips. So the action of A on a basis state is just to add itself to the basis state mod 2. So it just flips the bits. And B, we saw it acts trivially. So Z on 0 doesn't do anything. Z on 1 picks up a -1. So whenever this B is 1, you're applying a Z on that qubit. And if that qubit is also 1, then you pick up a -1. That's what this is saying. So whenever both B is 1 and the corresponding entry in V is 1, you pick up a -1. So this is the action of DAB on a basis state. Okay. So it's probably already clear, but just to make it more clear, so the Heisenberg-Weil group is just all these fourth roots of unity multiplied by DAB, and this EAB notation is just that. So we saw this XZY example. So you would write that, for example, as 1, 0, 1, 0, 1, 1. So if you just stack them one below the other, it makes it easier to look at it. So if you look at the first qubit, only the X component is 1, so you're only applying X. For the second qubit, you only have the Z component is 1, so you have a Z. And if both are 1, because this is for a Hermitian matrix, you have a Y. So if I wrote for DAB, this would be XZ, but for EAB, this is just Y. So all you need to take away from this slide is that Pauli matrices can be thought of as a pair of binary vectors, A and B. Or if you want to just concatenate both of them, it's a length 2n vector. And this is the notation that maps Pauli matrices, that maps the binary vector to the Pauli matrices. This is very convenient, and this binary notation AB is what establishes a coding connection, a classical coding connection, as we'll see in the upcoming slides. Okay, so this is not just a shorthand notation. In fact, you can make it an isomorphism. So the two key properties we see is that once you have this binary notation, when you multiply two Pauli matrices, the corresponding x component and the z component just add mod 2 for DAB, and you get this additional phase. But basically, up to this phase, multiplication of two Pauli matrices in the unitary domain is just like adding binary vectors in the binary domain. So this is so the mapping to the binary vectors is preserving the structure of the group. And the second structure we saw in the group is that Pauli matrices either commute or anti-commute. And so when you multiply two Pauli matrices in one way, you can swap the order, but then you pick up this -1 to this inner product. And if you see, this inner product is kind of special. So it's not the usual inner product where you would say take inner product between A and A prime and B and B prime. In fact, you have to swap. So you take the inner product between B and A prime and A and B prime and add them. The reason for that is quite simple. It's simply because this phase is coming from the fact that, for example, xz equals minus zx. So because x and z anti-commute, you only have to see for which qubits you have both x and z. So here, this is the x component, whereas here, this is the z component. So that's why you interact A and B prime. And this is the z component here and the x component there. That's why you're interacting those two. So that's the reason for this inner product. And we call this the symplectic inner product as defined in this paper. So for two binary vectors, AB and A prime B prime in length 2n, so the symplectic inner product is defined as this sort of inner product. And you can actually write it like this. So for normal inner products, there is no omega. You will just have AB, A prime, B prime transpose. But for the symplectic, you just introduce this omega, which swaps the order. So this is formally called the symplectic form or the symmetric bilinear form. Therefore, when you map to the binary vector space from the Pauli matrix to the binary vector space, you see that two matrices commute if and only if this inner product is 0 mod 2. So if this is 0, they two commute. If this is 1, they anti-commute. And that's exactly the structure in the Pauli group. Two matrices either commute or anti-commute. And we have this binary addition. So therefore, if you ignore this global phase, this I to the kappa, then the map from DABs to AB is an isomorphism. So hopefully that was clear. So the points I've said here is that any Pauli matrix can be mapped to a binary vector, and two Pauli matrices commute if and only if the binary vectors have symplectic inner product 0. They anti-commute if the inner product is 1. So that's what you want to keep in mind. Okay, with that general notation, so let's define general stabilizer codes. So a stabilizer of R dimensions is given by R generators. And because it's a commutative subgroup, they have to be mutually commuting. Each Pauli matrix can have a sign, which is plus or minus 1, but minus the identity is not allowed to be in the group. For a reason that will be apparent soon. So this is how you define a group. So they are generated by R commuting Pauli matrices. And note that because the Pauli matrices commute, AI, the symplectic inner product between AI BI and AJ BJ has to be 0 for any pair IJ. Okay, and then how is a code defined? So a code is defined as the subspace which are the +1 eigenvectors of all the elements of the group. So that's how we define the code. So it's the +1 eigenspace or the space fixed by every element of the group. Now you can make this ladder sort of. So you have this base, which is just the identity, and then you have this stabilizer group, which sits inside the Pauli group. So it's a commutative subgroup of the Pauli group. It has R dimensions. Now you can define something called as the S dual. And the reason we use this dual notation is because there is a mapping from the stabilizer code perspective. So we we wrote polymatrices as a pair of binary vectors, but there is a natural representation in the GF4 world. So the Galois field with 4 elements, so 0, 1, alpha, alpha squared, or 0, 1, alpha, 1 plus alpha. So in that space, you can map I, X, Z, and Y to 0, 1, alpha, 1 plus alpha. And then the group structure is exactly preserved under a specific inner product in the GF4 space. So that is a GF4 formalism, which you can read about in this paper. And so in the GF4 formalism, the S is actually an additive code. So it's not a linear code over Z4. Once you map these binary vectors to the Z4 world, it's an additive code over Z4. And the reason it's additive is because, for example, if you take two elements of this group, so how do you generate the group? You just take two elements and multiply them. And when you multiply them, the binary vectors just add. But note that you're not multiplying each element by any scalar. And that's what would correspond to if you define linear codes over GF4, because you would allow multiplication of a vector by a field element, but that has no interpretation here. The only interpretation is you can multiply two matrices and then the vectors add, and that's the additive property. So stabilizer codes are actually additive codes over GF4, and then you can define a dual in that space, which you can now pull back to the unitary world. So what does it mean in the unitary world? It just means that S perp is all the polymatrices that commute with S. So let's maybe look at an example. So let's go to our 311 code that we saw yesterday. So we had two generators, ZZI and IZZ. And if you do this EAB notation, there is no X component. So the X component is 0. And for ZZI, we have 110. And for IZZ, we have 011. So that's the stabilizer group. So what would be S perp in this case? It would be all polymatrices that commute with these. So for example, you can think of, so obviously any Z, a single qubit Z, will obviously commute with both of them, right? Because Z and Z commute. So Z on the first qubit or Z on second qubit or Z on the third qubit will commute with this group. And so that belongs to S perp, but it is not in S. So Z on a single qubit is not a stabilizer, but it does commute with the group. So that's what S perp means. And the distance of the code is defined like in the classical case. It is defined as the minimum weight of an undetectable error. So classically, we define distance by, like if you look at the parity check matrix of a linear code, we ask what is the minimum number of linearly dependent columns in the parity check matrix. That's basically asking what is the minimum weight of an undetectable error. So it's the same definition, but now we have to see a key point. Here, an undetectable error is something that is in S perp, but not in S. Why is that? So we saw that we can detect an error only if it anti-commutes with at least one stabilizer. Because remember, when we measure syndromes, when we measure stabilizers, we'll see a -1 eigenvalue only if the actual error anti-commutes with your stabilizer. So if the error doesn't anti-commute, for example, like if this error happened on your code, it commutes with your stabilizer, so you won't be able to see it. So this technically belongs to S perp mod S, and that's why the distance of this code is 1. So it's a trivial code because it cannot detect Z errors. It can only detect X errors. So hopefully that was clear. And now I'll again go through the 311 code from yesterday and go through these things. But is there any question from this slide? Because this is key. The notion of a stabilizer and the dual is key.
Okay, so maybe having some trouble following this S perp and its relevance, and
Okay.
also that of GF4. So maybe a little, could you go through it again?
Yes.
For the specific, for the example at least.
Yeah, sure. Actually, maybe I'll yeah, for the interest of time, maybe I'll skip the GF4 part. I just wanted to mention it because it's relevant, but explaining it would take some time. But so let's ignore GF4. I'll go through S perp again. Is that fine?
Yeah.
Okay. So so in group theoretic terms, S-perp would actually be called the normalizer of the stabilizer group inside the poly group. Meaning, so put in another way, once you have defined this S-perp group, S is a normal subgroup of S-perp. So if S is a normal subgroup, we know from the definition that left cosets have to be equal to right cosets, but poly matrices only commute or anti-commute. And so if you reinterpret that definition of a normal subgroup, that means that every element in S-perp commutes with S. And so if we go back to this example, so we have two stabilizer generators. So Z on the first two qubits or Z on the second two qubits. And when you multiply them, that's also a group element. That would be Z on the first qubit and the third qubit. Now with all, so these are all purely Z tensor products of Z matrices. And so any tensor product of Z matrices will commute with every element of this group. In particular, a single qubit Z matrix will commute with the element of this group. And therefore, this belongs to S-perp. Now you need to check whether inside S-perp lives S. So technically ZZI is also an S-perp. IZZ is also an S-perp, but they already belong to S. And we only care about S-perp minus S. And that is because those are like the pure errors. So anything in the stabilizer, when it acts on your code state, it doesn't change the code state. So it's technically not an error. It's a trivial error. So that's actually the difference. In the quantum case, there is this degeneracy of the stabilizer. In the classical case, the only error that doesn't affect your code word is the all zero error. Whereas in the quantum case, any element of the stabilizer, if that was the actual error in quotes that happened, then actually nothing happened. And so we only care about errors that you can't detect, which means it has to commute with your stabilizers, because that's when you measure the syndrome, the error would have commuted, so the eigenvalue will still be +1. You won't detect the error, but it still affects your code space non-trivially. Is it better now? Is it clearer now?
Yes. So as I understand it, the elements in S-perp/yes are the undetectable errors, right?
Yes.
Okay.
Yes. Yeah. So yes. So if an error from just S acts on your code, nothing happens. So you're fine and you won't detect it, but it's fine. But if an error from S-perp minus S happens, you will still not detect it, but it's a problem.
Thank you.
Let's actually go through the 3-qubit codes. I put the slides again here from yesterday. So for the 3-qubit code, we defined the stabilizer as the ZZI and IZZ, and then our code space was spanned by these two basis states. So any linear combination of 0, 0, 0 and 1, 1, 1 was your code space. So from the notation of the previous slide, V of S, which is the stabilizer subspace, the code subspace, is spanned by these two, and that's this psi bar is from V of S. And so we talked about the parity check. And so for the basis states, we saw that ZZI and IZZ only define two stabilizers on 3 qubits, which means there is again a space for one more qubit to live. And that's how the code subspace is defined. But if you want to exactly define this 3-qubit state 0, 0, 0, then you have to add another generator, and you can take that to be ZII. And this is actually the logical poly operator, because so this is the extra stabilizer for 0, 0, 0, and for 1, 1, 1, the extra stabilizer is minus ZII. And that's why this is like the logical Z, because remember, so what is a logical Z supposed to do? It is supposed to act trivially on 0 state, but pick up a -1 on the 1 state. That is the definition of a Z. So when we say a logical Z, that means there is a 3-qubit physical operator which acts trivially on the 0 state on this state, but has to pick up a -1 here. So ZII is the right operator because ZII acting on 0, 0, 0 doesn't do anything. but ZII acting on 111 picks up a -1. So as we'll see later, we also saw this yesterday, but this is the logical poly. And technically the logical polys live in S-perp. So I'll make that clearer now. So we saw that, and we saw this useful way of looking at states versus operators. So when you evolve a state through a unitary, the stabilizer gets conjugated. And using this notion,
yeah,
and
so
using, yeah.
any idea as to what will be the size of this esper?
Yes, so the size of S-perp, so it is just the dual in the space. So if you think of it as in the GF4 space, so this will, right, so it will just be n minus r. So if r is the dimension of the group, this will be of size n minus r, like dimension n minus r.
Yeah, thanks.
Yeah. Right. So we saw, yeah, so whenever errors happen, the way to compute what is the syndrome is you take the stabilizer and conjugate it by the error. So because take this unitary to be the error, if the error acts on the code state, then the stabilizer gets conjugated by the error. And so if x1 acts on the code, then you conjugate the zzi by x1, x and z anti-commute, so you pick up a -1. So that's how you compute syndromes. It comes from conjugating the stabilizer by the error. And then we saw that we defined these different subspaces whose projectors add to the identity. We call this the resolution of the identity, and the errors just move you between these different subspaces. So you start in the +1 +1 space, and whenever errors happen, the syndromes get changed to one of the +1 -1 combinations, and then you apply the correct correction operator, you get back to the subspace you want. Finally, we saw this notion of thinking of a qubit as a pair x and z instead of a single qubit, a length 2 vector. So any qubit is just abstractly it's just a pair of x and z, and whenever a unitary acts on it, all you have to study is how it acts on x and how it acts on z, and then you have defined the evolved qubit. So if you have k qubits, each qubit has a pair x and z. They have to anti-commute, but x on one qubit and z on a different qubit have to commute, and similarly, yeah. And then we saw this encoding circuit, and then we saw that the logical x in this case, so x applying an x here at your logical qubit is equivalent to applying xxx here. So applying x here and then encoding is the same as first encoding and then applying xxx. That's the definition of a logical operator, in this case a logical poly. And like we saw a few slides before, the applying z here and then encoding is like applying z here, if like encoding and then applying z here. So this is the logical z. And but once you have defined these, we are always free to multiply by stabilizers because stabilizers don't change the state. So technically, each logical poly is a coset of the stabilizer group inside the poly group. And right, so this is already what we saw. So for the basis states, you have an additional stabilizer. And this additional stabilizer, as you can see, comes from the logical z. So you just take the logical z and multiply by -1 if you're writing the stabilizer for the logical 1 state. If it's the logical 0 state, this -1 to the 0 is just 1. So always a stabilizer group can be appended with logical z operators with appropriate sign to define the maximal stabilizer group that uniquely defines a logical basis state. Hopefully that was clear. And so what have we seen so far? We saw that once you have defined a stabilizer group, if you want to define the unique stabilizer maximal commutative subgroup that defines a logical basis state, you just add all the logical z operators with an appropriate sign that is modulated by whether the bit is 0 or 1. And this in fact is a nice way to actually initialize a code state. So in the lab, let's say you want to encode into your subspace, right? So one way you could do is you can take your information. So let's go back to this slide. So you can first take your information, add some ancillary qubits which are in the 0 state, and then run your encoding circuit to run your encoder and to get your code state. The other way to do, which can usually be made more fault tolerant, I think, is you take any state. So you initialize your system in any state on small n qubits. And then you know that each time you measure a stabilizer, you actually project onto the eigenspace. So you measure each of these stabilizers. If you get a -1 result, you apply the correct correction operator to make it +1. So you make sure that the measurement of the stabilizers is giving you +1s. And after you do that, you have now projected onto the code subspace. But let's say you want to specifically initialize to a logical computational basis state. That means you have to measure more things. So think of each measurement of each stabilizer as projecting or as like cutting the space into half. So initially you had n qubits. So the space was of size 2 to the n. You measure your first stabilizer, you cut by half. You measure the second stabilizer, you cut by half, and so on. So once you're here, you are in a 2 to the n minus r dimensional space. That's your code subspace. But now you actually want to keep cutting down onto a specific logical basis state. And that means you measure your logical z. You'll again get a ±1 result. And you keep going until you measure the k logical. Now, once you have done the whole process, you have a unique state. And which computational basis state that corresponds to is given by this sequence of -1s, -1s and +1s that you get when you measure your logical z. So that's a nice way to actually initialize a code state. Okay, so we have got that. And then if an error happens, which is given by two binary vectors E and F, then we saw that the syndrome is just whether this commutes or anti-commutes with each stabilizer. And the binary vector formalism, that's the symplectic inner product. So you just take E and F, and because of omega, you swap the order. So you have F first and then E, and then you just take the inner product which each generator. So this is like classical parity check, right? Because classical parity check, we just do, you send a code word X, you get a vector Y. The syndrome is just HY transpose. That's exactly what we're doing here, except that you don't get to observe Y. Because it's a quantum state, you don't get to observe Y. But once you have measured the syndrome, the way you interpret it is as the result of these inner products. And finally, this is the code projector, and summing this code projector over all possible epsilon i's gives you identity. That's the resolution of the identity. So is this general stabilizer formalism roughly clear?
So quick question. So when you say you want to prepare that particular logical state.
Yes.
So you take an arbitrary n-dimensional qubit, and then you take this specific set of operators which you have, right?
Yes.
The code space things, as well as this -1 power x1 into z1 power and so on.
Yeah.
And then you do whatever you said. So
exactly. Yeah. So just to be more clear, so these epsilon ones are defining your exact group, and if you have this particular state, these will be the sequence of signs. But of course, so you initially have a state and you keep measuring, and you might keep getting like random ±1 results. So you don't know what results you're going to get. So every time you get a result, you're going to plug that sign here, and that gives you which stabilizer you have projected to, and also in that stabilizer, which logical state you are in. And remember so the measurement results correspond to these signs. So you initially don't know these signs. You only know which operator you want to measure. But once you measure, you get the sign from the measurement result, and you plug that as epsilon1, epsilon2 up to epsilon r, and that gives you which part of the resolution you are in. So that already tells you which code you are in. And inside that code, after you measure the Z1 bar till ZK bar, it gives you signs that tells you which exact computational basis state you are in. So that's my full statement. Yeah, there's a question in the chat. Let me, as we can have a combination. Um, so so far, so I'm looking at the question by Rohan Sharma. So to be clear, so when I define codes, we define always in terms of pure states because the code is defined in terms of specific pure states. So mixed state, I think of it as an abstract concept which helps you deal with a probabilistic system. If you don't know what exact state the system is in, you have a probabilistic mixture of different pure states. But of course, so when you say mixed state, I'm thinking of it as qubit that decohered. So the initial qubit would have been in your code, but the mixed state technically doesn't belong to your code. So I don't know what you mean by whether this formalism holds for mixed states. Is my question clear? Like, Rohan? Okay. Yeah. So I mean, quantum theory is linear. So whenever you have mixed states, if you're somehow thinking of the mixed state as a mixture of code states, then of course you can apply this formalism to each state, and then you have a probabilistic mixture of code states, which is fine. Yeah, so by linearity, anything you define for pure states can be extended to mixed states. But usually we think of stabilizer codes as being defined on by pure states. Okay, let me continue. Okay, so at this point, I just want to advertise one classical coding connection. I'm not going to delve too much on this, but I just wanted to put it because I thought it could be interesting for some of you. So classically, for people familiar with classical coding, you might have heard about Coda codes. These are actually unions of cosets of Reed-Muller codes. So these live inside the second order Reed-Muller code. So we were able to do this both classical to quantum and quantum to classical connection using these Coda codes. So going from classical to quantum, we were able to show that these Coda codes, which are nonlinear binary codes, but can be made linear over Z4 using the gray map. So we were able to show that the symmetry group of these Z4 linear Coda codes can be mapped to some unitary matrices in the quantum domain. And those unitary matrices form what's called a unitary 2 design. So unitary 2 design is an ensemble of unitary matrices. It's a mixture of unitary matrices that satisfy some statistical criterion. And these unitary 2 designs can be used for something called as randomized benchmarking, which is a popular protocol to benchmark quantum computers. So unitary 2 design is a key tool there. People usually construct, like unitary 2 designs in a random fashion, whereas here we were able to use the symmetry group to give a deterministic construction of a 2 design. So this is a coding connection with classical codes, but actually I'm not doing quantum error correction here. That's what I want to emphasize. So using classical codes, there are also applications in quantum which doesn't have to do with quantum error correction. So that's what we did from classical to quantum. And in the same paper, actually, I like this derivation a lot. So we were able to use the stabilizer formalism, which I just introduced to you, these code projectors and these commuting polymatrices, etc. We were able to use the stabilizer formalism to write like a half-page proof for deriving the weight distribution of Coda codes. So if you actually look in, for example, the textbook by McWilliams and Sloan, there's a long derivation for the weight distribution. But once you get accustomed to this stabilizer formalism with this basics of this formalism, actually it's possible to very nicely derive the weight distribution. So I encourage you to look at our paper. So this might be a connection that you might be interested in. And we are actually hoping we can pursue this further and establish more connections with classical coding. That doesn't have to do with quantum error correction necessarily. Okay, so with that, that's an aside. Let's get back to stabilizer codes. CSS codes are a specific form of stabilizer codes. So this is where you can see classical codes directly popping in. So remember, so this was our stabilizer matrix. So we saw that each row gives you a generator for the stabilizer group, and any pair of rows must have symplectic inner product 0 because the group is a commutative subgroup. Now stabilizer CSS codes are the special case where you can there exists a generator for the stabilizer where each generator is either a purely Z-type operator or a purely X-type operator. So this is just 0. That's what I mean. And this matrix is with respect to this binary notation AB. So each row is like EAB. So A is the X part and B is the Z part. So these rows gives you a pure X-type operator, and these rows give you a pure Z-type operator. So technically how this construction comes about is you take two classical codes, C1 and C2. C2 is a subcode of C1. So C2 is of dimension K2 and C1 is of dimension K1 larger than K2. And then you take C1 dual and then C2 dual. Now the generator matrix, so the generator for the stabilizer group, the X-type operators come from the code C2, and the pure Z-type generators come from the code C1 dual. So given two classical codes where one lives inside the other, there is a quantum CSS code, which is a stabilizer code defined by this sort of a stabilizer matrix. And what's nice is that you can show, it's not very hard to show that if the dimension of if the distance of C1 and the distance of C2 dual is at least 2t plus 1, then which means these codes can correct t errors, then the quantum code can correct any t qubit poly error. So formally, so C1 and C2 dual are what are used to correct errors. And you can see that C2 is giving you the X stabilizers and C1 dual is giving you the Z stabilizers. So, so if you have a Z error, the X stabilizers will detect it. If you have an X error, the Z stabilizers will detect it. And so here is an example of a 642 code. So you have just two generators. One is X on all qubits, no Z, and the other generator is Z on all qubits, no X. So this is a way to construct quantum codes using two classical codes. But of course, you have this constraint that one lives inside the other. Or the other way to see it is that C2 and C1 dual have to be orthogonal to each other, because these are X-type generators and these are Z-type generators. And these give you stabilizers, which means they have to pairwise commute. And if an X and a Z have to commute, so an X operator and a Z have to commute, then the symplectic inner product between something here and something there should be 0. But the symplectic inner product is between the X and Z here and the Z and X there, but these are zeros. So basically it's the inner product between this and that. And therefore, whenever you have two codes where one is orthogonal to the other, there is a way to define a CSS code. There are actually many classes of CSS codes already defined. In fact, most examples you will see in the literature are CSS codes. So one problem you could think of, for example, is so LDPC codes have been recently quite popular in quantum for a natural reason. So so think of C1 and C2 dual as being LDPC codes, which means their parity check matrices are sparse. So the parity check matrix of C1 is the generator here, which means the parity check matrix of C1 is this guy here. So it's giving you Z stabilizers. And the parity check matrix of C2 dual is the generator of C2, and those are giving you X-type stabilizers. So if C2 dual is an LDPC code, then this G2 matrix is also sparse. So one challenge is to construct LDPC CSS quantum codes constructed from two classical LDPC codes. But classically, we define LDPC codes as like these random sparse matrices. But here you have this constraint that these two sparse matrices have to be orthogonal to each other. So that makes it quite hard to actually construct LDPC codes. And for some beautiful constructions, you can look at the work by Jean-Pierre Tillich and Gilles Zimor. So Tillich and Zimor, they've written many papers together, in both in classical and quantum coding. So you can look at their papers. They are in France. So Tillich and Zimor have some quantum LDPC constructions, quantum expander code connections and constructions using the CSS formalism. And they are able to actually also produce, linear rate codes and like square root distance, I think. So the challenge is to improve those constructions, make better decoders, and compute logical operators for these codes, etc. So that's a very active research area. So so LDPC codes with good logical operators, fault tolerant logical operators is a very active research area. Okay. Now just okay. So in the so I'll. Yeah,
So
maybe in the interest. Yeah.
So you mentioned that the logical operators, you want them to be fault tolerant. So
Yes.
how is that
defined?
Placed? Yeah.
Yes, I'll get to that. I'm going to explain that a little more in a future slide. I'm getting to that. Okay, so I was yes.
I mean, is there any reason to pick these LDPC codes here? Means any clear advantage?
Yes, good question. So once you have C1 and C2 dual as LDPC, then this matrix and this matrix is sparse. And remember, in quantum, we actually don't get to see any received code word. The only way to know if errors have happened is by measuring syndromes. And so when you want to measure syndromes, you have to measure poly operators, which belong to your stabilizer. And the nice thing about LDPC is that yes, by the definition of LDPC, the weight of a poly operator, which means the number of qubits in which it is acting non-trivially, is fixed irrespective of the code size. It doesn't scale with n, and so it makes it much easier for experimentalists to measure these operators. If the operator is of fixed weight, which doesn't scale with the code size, so you have a code family where the size of the operators you have to measure is fixed. And that is extremely useful for experimentalists, because measuring a very large number of qubits at a time, and a poly operator that acts on many qubits at a time, is experimentally very challenging. And so that's why people are very excited about LDPC codes these days. Is that clear?
Yeah, thanks.
So yes, that's one motivation, but yeah, that can also be other reasons. But that's the main motivation. Okay, so initially I was planning to go through the 642 construction, but I think I'll skip that to talk about more important things. So you can, I'm happy to share these slides. Hopefully they'll be self-explanatory. But basically what I want to highlight is whenever you have a CSS code, there is an explicit way to write a logical basis state. And so once you write down a generator matrix for this code C2 and C1, C2 lives inside C1, and this is the generator for the coset. Then at a high level, what I want to highlight here is that when you have a logical basis state, so the zeros and ones here are just modulating whether one of these rows is added to the state or not. So the general form of a logical basis state is you sum over the coset of the code C2 inside C1, and the coset generators are linear combinations of these last four rows. So the first row is giving you the C2, and these remaining rows are modulated by your logical information. And so you just sum over the coset, and you can check that the stabilizers actually fix this state. I'm not going to get into much detail, but I just want to emphasize that for stabilizer codes, it's also possible to write down the logical basis states explicitly using these classical generator matrices. And by using that connection, you can also write the logical polys, the logical X and Z, using these classical generator matrices. And it's also not very hard to check, so I'm going to skip this part. Okay, so far I've introduced this binary notation for polymatrices, and that is the main classical coding connection. Because when you, for example, define CSS codes, these binary matrices from the classical coding world is what is giving you the quantum stabilizers. So we have introduced that, and we saw what a normalizer is, what logical polys are, and we saw the 642 example. So hopefully you have a good big picture of what's going on. Okay, now we have to move beyond polymatrices because the unitary space is much larger than just polys. So here is another ladder. So we already saw a ladder where we have a stabilizer, and then in between we had this S-perp, and then we had polys. But now ignore S-perp. So you have a stabilizer, and then on top of it you have the polymatrices, and on top of polys you have what's called the Clifford matrices. So it's again the same normal subgroup structure. So just like S was a normal subgroup of S-perp, polymatrices form a normal subgroup of this Clifford group. So put another way, Clifford group is defined as the normalizer of the polymatrices in the unitary group, which just means that when you take any polymatrix and you conjugate by a Clifford, you get a new polymatrix. And these are some of the standard Clifford operators. We already saw the Hadamard and the control not when we talked about encoding the 3-qubit code. And there is this phase and control Z. So these are like the standard gates that people think of implementing in the lab. So of course, there is some variation with respect to what architecture you're working with, but in general, these are the matrices people think about. So the Clifford group is just all matrices in the all unitary matrices that map polymatrices to polymatrices under conjugation. That's the definition. But of course, Clifford is not all of the unitary space. There is still some space left. There are still more matrices left between Clifford and unitary. So this is a more precise way of writing down this Clifford action. So you take a polymatrix, you act by a Clifford. By definition, you get a new polymatrix, but more specifically, it's a linear transform of this binary vector. So you started with a polymatrix that is specified by two vectors A and B. The new polymatrix is the linear transform, but it's not any linear transform. It is invertible and it has to be symplectic, which means it satisfies this condition. This condition basically says that before and after acting by F, the pairwise inner products, the pairwise symplectic inner products remain the same. So this is like, if you think of a complex vector space and if you apply a unitary matrix, you know that a unitary matrix preserves the norms of the vector and preserves the angles between two vectors. So, and this is the same notion here. So before and after applying this symplectic matrix, the inner products between two vectors is preserved. So FG is the symplectic matrix. It's also invertible. And so you can think of Clifford operators as just these symplectic matrices. That's all I want to highlight here. So polymatrices are these binary vectors with the symplectic inner product, and Clifford operators have a homomorphism to these binary symplectic matrices. And this is a huge reduction in complexity in representation because this Clifford unitaries are 2 to the n by 2 to the n, 2 to the small n by 2 to the small n, whereas these binary symplectic matrices are just 2n by 2n. And in fact, you can capture most of the structure in this space. So it's a very efficient homomorphism. Okay. Again, I'm going to skip this slide because I'm not going to concentrate too much on Cliffords. So once you define Cliffords, you can also define logical Cliffords, meaning you have logical qubits. You want to do a Clifford operation here. You can ask the question of how do I realize in the physical space? And so you can go do this translation. Again, I took the 642 code as an example to show the C0, but I'll also leave this in the interest of time. Maybe I'll highlight one thing because there is some classical connection that you can think about. So, take it from me that this is the right representation of the logical basis state for the 642 code. And let's say you're interested in doing this C0 operation on the logical qubits. So you have the first two, you have 4 logical qubits, but take the first 2 and say you're doing the control not that where the control is on the second qubit and the target is the first qubit. So you want to do this control not. And this is an invertible operation on this binary vector space. So that is binary, that invertible transformation is given by k. So you want to implement k, x goes to x times k. So meaning you want to take this x to x times k. So you take that, you take x to x times k, and you ask the question of, now you have this, so this is the logical operation you want, but in the lab you can only act on the 6 physical qubits. So we are trying to figure out what the 6 qubit operation is. So you ask the question of, I have k times g. Is there an invertible 6 by 6 matrix Q such that k times g is g times q? And once that exists, you can substitute that here. And then you want to write this in this form because this Q has to act on all the qubits. It cannot act only on the second part. It's physically impossible. So if you want to write this Q as acting on everything, then that means C times Q should be just another code word in C2. In other words, Q has to be an automorphism of the code C2. So once Q is an automorphism of the code C2, and it also preserves this coset structure, then you're basically shown here that using this Q, which you can act on the physical 6 qubits, you have effectively realized the operation x goes to x times k. So for CSS codes, you can always look at it like this. Whenever you want to do a logical C0 type operation, you can always ask this question and try to find a Q. So you can actually look at this paper where they actually look at all Qs which are permutation matrices. So they're permutation automorphisms of classical codes. And they use that to get some free operations in the quantum case. Because Q, if it's a permutation, then that just means you're taking the 6 physical qubits and just permuting them. You're not, so here, unfortunately, you have some physical C0s that you have to do. But physical permutations are like, like free because you just have to relabel qubits. And so you can actually use automorphism groups of classical codes to get these sort of free operations. So this is actually a widely open area. There's not many papers written except for this, where people explore how to get free operations on CSS codes from the knowledge of automorphism groups of classical codes. So that's something I wanted to mention. But in general, we have this logical Clifford synthesis algorithm. Unfortunately, this procedure can only work for these C0 type things. But if for more general logical Cliffords, you need a more general algorithm. And so people had done this for specific codes and specific operations in the literature, but they didn't seem to have a general algorithm. So we were able to propose this general algorithm where you can feed in a logical Clifford and the stabilizer and the logical polys. And the algorithm gives you all equivalence classes of physical circuits that implement that logical Clifford. So this is a very general algorithm you can apply to any stabilizer code. So the implementation is here, and you can read more about it here. The algorithm is efficient because it uses these symplectic matrices representation for Cliffords. So the algorithm is quite efficient. Okay. Right. So this is a central result. So yeah, before I continue, maybe I'll ask. So can I go for like 5 to 10 more minutes? Is that okay?
Sure.
Thanks. Okay, so the Gottesman-Null theorem is one of the early results and key results in quantum computing. It says that it says the following. So let's say you start with this n qubits in the 0 state, and your circuit only consists of Clifford operations and Pauli measurements. And together, these Clifford operations and Pauli measurements are commonly called stabilizer circuits or stabilizer operations in the literature. And what Gottesman-Null showed is that so if this is the only thing that your circuit is doing, then it can be efficiently simulated classically with like complexity n squared or n cubed. So it's a polynomial simulation algorithm. So if you only had this, there is no quantum advantage. You can efficiently simulate on a classical computer. Of course, this is all asymptotics. I mean, in the finite case, n cubed can still be quite big, but so and the key idea is just to you get one way to view this. So Aronson and so this is the theorem by Gottesman and Null, And Aronson and Scott Aronson and Daniel Gottesman actually wrote down what's called the CHP algorithm that is sort of a manifestation of this theorem. So and the basic idea there is to they don't talk about it in terms of symplectic matrices, but basically anytime, so you have an initial state, which is the all zero state, and we know that the group that fixes that state is the Z group. So the Z on any qubit fixes the zero. So this is the maximal stabilizer that uniquely fixes the state. And the idea is just to conjugate. So if you only had a Clifford circuit, just conjugate the Z by a Clifford, which is equivalent to multiplying the binary vector by a symplectic matrix. That's all efficient. And whenever you want to measure a poly, there is a nice way to also do that. So efficiently, you can simulate these circuits. Therefore, we need non-Clifford operations for a quantum advantage. And in fact, there is also this important result that says that if you can do all Clifford gates, and if you can do any one non-Clifford, then together they become dense in the unitary group. So you can arbitrarily approximate any unitary up to any good approximation using all Clifford gates and any one non-Clifford. So this is also an important result. So I wanted to mention that. So basically the idea is you need non-Clifford operations, and specifically once you have a code, it's not enough to do logical Clifford operations, but you also need logical non-Clifford operations. So extending our Clifford synthesis algorithm to non-Cliffords is challenging, so we aren't able to do that. But instead, if you look at the literature, one of the common ways of doing logical non-Cliffords is using what's called this magic state distillation. So right now I'm just giving you some hints into important concepts because I think these should be covered in a quantum error correction sort of tutorial. So I'm just giving pointers to important concepts in the literature. There are also some recent developments. Okay, so here the idea by Brabi and Kitaev is very beautiful. So they realized that, so let's say you have some data stored in a logical state. So this belongs to some code. And so they are working with this resource theory that Clifford operations are free, meaning Clifford operations you can very precisely realize in the lab, which under some considerations is reasonable. So that's their assumption. So you can do these stabilizer operations, which means the Gottesman null operations, the operations that can be efficiently simulated. So those Clifford operations and poly measurements, they assume you can do very precisely, but non-Clifford operations are not free. So what they do is that instead of directly implementing a non-Clifford unitary as a circuit, they realize that you can, for any non-Clifford operation U that you want to act on your data, they define a resource state called a magic state. So this is independent of the data. So without even knowing the data, you can prepare these states in a factory. So there is a procedure to prepare these states. And then they show that you can, using only these stabilizer operations, meaning Clifford operations and poly measurements, and this resource state, think of it like a catalyst in chemistry. So putting these together, you can actually realize the desired operation on your code, on your data. So this is a very different way of looking at computing. So instead of directly doing the unitary, you're doing just initializing this resource state, which can be prepared separately. And to increase the fidelity of these states, meaning to increase the quality of these states, they use some CSS codes to take noisy input states, and they convert them into higher quality states using a process called distillation. And this distillation comes from some specific types of codes. So this is also a literature that you might be interested in looking at, because there is some classical coding connections, which I'll highlight now. But yeah, so magic state distillation is a very important procedure. But the problem right now is that it's very resource intensive. So any methods to reduce the resource intensiveness of this distillation procedure is super useful. Okay, right. So what is our idea? So if you think of my first slide from yesterday, I asked this question. I had this commutative diagram, and then I asked this question of what structure is required so that certain gates preserve the code space. So the idea here is, so in this distillation procedure, they use codes where this unitary that you want to implement can be implemented using an operation that splits it to individual qubit operations, which is called transversal. So if you have like 5 qubits, and if your unit tree can be implemented as individual operations on the 5 qubits, meaning you're not interacting 2 qubits, then that's called transversal. And that property doesn't propagate errors. So whenever you have errors, because the qubits are not interacting, the operation is fault tolerant, meaning it doesn't spread the errors. So we asked the more generalized question of when does doing a particular operation in the lab preserve the code space? And the way we look at it is that because any operation can be written as a combination of polys, we understand the action on these poly matrices, and then we go to these stabilizer codes, and then we take this understanding and apply it to code subspaces, and then compute what code structure is required. So our way of looking at it is different, but it's very related to some of the ideas that's used in distillation. So there's a long literature on distillation. I'm just giving it as pointers, but I want to highlight these 2 papers. So this paper by Bravi and Ha, where they talk about distillation, they introduce this notion of tri-orthogonal codes, which is actually a classical code family. So you can look at this paper to see how you can construct. So good constructions of these types of codes is highly sought after. One recent construction is punctured. So Tillich and Anirudh Krishna used polar codes, and they used punctured polar codes to construct tri-orthogonal codes. And these punctured polar codes come from Tillich's formalism called these decreasing monomial codes, which is a classical coding family. It's sort of a smooth extension of Reed-Muller codes. So I encourage you to look at these things. And in our paper, we also make connections to these other works. Okay, so let's skip these. Right, so in the last couple of minutes, I'm going to show you a classical coding problem and then end there. But to mention why the coding this classical problem I'm going to state is important. So we saw that Cliffords are generated by these 3 rows, these kind of matrices. And the non-Clifford gate that's commonly implemented is called the T gate. But the problem is because it's a non-Clifford, there is no symplectic formalism for it. So it makes it kind of challenging to work with it. And so we actually first defined this formalism called quadratic form diagonal gates, which generalizes this operation for Cliffords. And then we are able to show that the T gate belongs to this formalism, and we give some properties. So this T gate is the usually used non-Clifford gate. And so coming to this fault tolerance, sorry, please give me like 2 minutes. I'm going to finish. The reason quantum error correction works is because of some key ideas. So we saw yesterday about this discretization of error principle. The other thing is this threshold theorem, which says that as a function of your coding scheme, if you can reduce the physical error rates of your components of your circuit below a threshold, then it is possible to do arbitrarily long reliable computation with not too much overhead. So this is a key result. And following on that, people have defined different error models. And surface codes, as you might have heard, is a popular coding family that people use, and they have some high thresholds. Fault tolerance, going back to your question, is just that between 2 consecutive error correction routines, you're going to do some operations. And you want to make sure that if you're using a T error correcting code, that any T faults in that sequence of operations don't spread catastrophically. So that's like the higher level definition. So when you get to the next error correction procedure, you have to make sure that if any T faults occurred, at the end of the procedure, it still remains as T faults so that you can correct it. So that's pretty much fault tolerance. And transversal operations is what I said. So it splits into operations on individual qubits. And so because you're not interacting between qubits, it means that it's naturally fault tolerant because it doesn't spread errors. But unfortunately, Easton and Kinnell showed that you cannot realize everything in quantum computing using transversal gates. So you can do some operations transversally, and then the other operations you have to find other fault tolerant methods to do. And the general sort of principle is Non-Clifford gates are hard to do, logical non-Clifford gates. So we usually do logical non-Cliffords using transversal operations, and other operations we do using other methods. Okay, so using this, we ask the question of when does T applied on all qubits preserve the code space? And that brings us to this coding family. So these are CSS codes, and you have a pair of codes like before, C1 and C2. The first condition you need is that the code C2 is an even code. And the second condition is that for every code word in C2, the dual of C1 consists of a self-dual code that is supported on this code word, meaning the non-zero entries in the self-dual code is a subset of the non-zero entries of X. So you need a coding family that satisfies these two. And if it satisfies these two, then applying the T gate, which is a non-Clifford gate, on all the code qubits preserves the code space, which is a basic condition you need. So this is the most, so that's how this is a new classical coding connection, and you get these code parameters. And the open problem we have is to construct a linear rate and a fairly good distance code family that satisfies these constraints. Because if we can satisfy this, then like I said, you can decrease the overhead for distillation by a large amount. So basically this gamma goes to 0 under these conditions. But I will leave the details for you to look on the paper, but this is the new coding problem we have that is inspired by fault tolerance in quantum computing. Okay, to summarize, I introduced the binary notation for polys. We saw these two examples, and we saw the Clifford synthesis, what the high-level idea of Clifford synthesis, and the Gottesman-Null theorem of efficient classical simulation. And then we couldn't extend our Clifford synthesis to non-Clifford gates. So we used this QFT framework that we introduced to construct codes that support T gates. And then we have this CSST problem, which is purely a classical coding problem. But the main trick we use is just to express unitaries in its poly basis, which people know for a long time. But in this setting, for constructing codes supporting gates, I think we were the first to apply this. Okay, so those are my a lot of references, and I'm happy to share the slides. Thank you.
Okay, thank you so much.
Yeah.
So I think this was a very educative experience for us.
Okay.
We are not that much into this area, so I think a lot of people would have appreciated it.
Okay. Yeah, I'm glad. Thank you for the opportunity, and yeah, thank you for encouraging me to give this talk. It was also good, good exercise for me to collect my thoughts and prepare slides. It was.
Yeah.
So feel free to email me anytime if anyone has questions, and I'll send the slides to Prasad, and I think he happy to share slides with anyone.
Yeah.
So Prasad, can I ask a quick question now?
Yeah. So we have time. I hope Narayan has time. Yeah.
Yeah, I'm fine.
Narayan, so thank you very much for spending time with us. And so my very quick question is, so the open problem that you stated, CSST problem.
Yeah.
Do you know anything about the existence of such codes? So such codes, do they even exist?
No, CSST codes exist. That's not the issue, and we also have some Reed-Muller examples in the paper. The open problem is really to get the scaling of the rate and distance.
Okay. Thank you.
Yeah. So for example, like there are codes where the rate is the number of logical qubits is fixed, meaning the rate goes to 0 very quickly, but the distance is still large, and it supports these T gates. So there are some like the extreme cases are sort of there. But for example, like the distance is trivial, the rate is good, and you have the T gates, or you have the rate being bad, the distance being good, but we don't exactly understand the trade-offs, and we don't understand what's possible and what's not possible. So the scaling is the open problem. CSST codes exist.
Okay. So at least for these extreme cases, what classical tricks were useful?
So one trick is this. So if you look at this paper that I told on triorthogonal codes, so that's one of the. They didn't have this notion of CSST because they were working with a sufficient condition, whereas where the CSST problem is a necessary and sufficient condition, sort of. So that triorthogonal trick, that family is. So the trick is to construct a code whose generator matrix satisfies the following two constraints. So any pair of rows is orthogonal, and any triple of rows is also has even overlap. And that condition, using those two conditions, they were able to construct codes which form a special case of the CSST family. So that's one of the tricks. And using Reed-Muller, so whenever you have a code defined by monomials, because we have these support conditions and you have a self-dual code in the support, etc. Because codes defined by monomials, multiplying by two monomials is like taking the star product between the corresponding vectors. So this monomial formalism is also very convenient to make code satisfy this constraint. But the problem is also that it seems like whenever we construct codes out of monomials, the rate always seems to be asymptotically 0. So in our paper, we have a Reed-Muller family. And so the number of physical qubits will be like 2 to the m. So n equals 2 to the m. But the k is like m choose r for some r. So this is coming from Reed-Muller RM. So the problem is m choose r doesn't scale as fast as 2 to the m. So the rate is asymptotically 0. So it seems like with monomial codes, it might be hard to get this linear rate. But those are the two, familiar tricks.
Okay, thank you.
No problem.
Okay, so if there are no further questions, then we can thank the speaker virtually and bring this to an end. Thank you so much. Yeah.
Thank you. Thank you for having me.